Let's look at our second approach
of a cylinder.
Suppose that I have some infinite line of charge. Now, we've very recently done that. We know that the electric field for an infinite line of charge is, let's see, two K times lambda over R, where lambda is the line charge density. Now, here's the sneaky bit. For this infinite line of charge, let us take a cylinder of radius r. Now, the electric field for an infinite line of charge is radially outward. So, if I look at this, and I want to find, the electric flux over the entire surface, that's the integral over the closed surface of E dot dA. But here, I have 1, 2, 3 surfaces. So I have to break this into 3 subcategories. The integral over E dot dA over area 1 plus the integral of E dot dA over area 2 plus the integral of E dot dA over area 3. Now, in this case, notice that the differential areas dA are all radially outward. So, on surface area 1, these two vectors are at right angles to each other. There is no flux through this side because no field lines cross that side. They stay in it. So, the flux through side 1 and the flux through side 3 are both 0. That makes life happier for us because suddenly 2 integrals are gone. And I've just got this remaining integral, which is, okay, the electric field of, let's see, I've got, okay, in each one of these cases, the electric field here is still parallel to dA, so E dot dA is just E times dA. The electric field is constant over surface 2, or its magnitude is constant over surface 2. So it just becomes E times A. So the integral over the entire surface of E dot dA is equal to the integral of the electric field, 2 times 1 over 4 pi epsilon naught times lambda, which is let me keep lambda for one more step, times 1 over r times the area. And the area for this cylinder is, okay, the circumference of this circle, 2 pi r, times its length L. Now, having L in here could be a problem, because this is supposed to be an entirely made up number. You know, the L is made up, it's entirely arbitrary. So, it darn well better not matter what that arbitrary number is. However, let me take this and write this as, okay, the line charge density inside that case is the charge inside the enclosed charge divided by L, the unit length. And we notice 2 and 2 cancels with 4. Pi cancels. R cancels. L cancels. So I'm left, in this case, with that integral is equal to the integral of E dot dA for this special Gaussian cylinder turns out to be equal to the enclosed charge divided by epsilon naught, just like what we had when I did this for the point charge. The entire surface integral just turns out to be Q naught, or Q enclosed, divided by epsilon naught again.